Asteroids are small worlds in the vast expanse of space, and they are ancient bodies composed primarily of rock and metal. Most of these celestial wanderers reside in a great ring that orbits our Sun, located between the planets Mars and Jupiter. This region is famously known as the asteroid belt. While many remain within this distant band, some have orbits that bring them much closer to our home planet, Earth. Others are flung into the far, cold reaches of the solar system. Today, we will embark on a journey to understand what asteroids truly are. We will explore their ancient origins, tracing them back to the birth of our solar system. We will learn about the gravitational forces that govern their movements through the cosmos. We will carefully examine the primary types of asteroids that scientists have identified: dark, carbon-rich relics, bright, metallic fragments. To understand asteroids, we must travel back in time to the very beginning of our solar system. Approximately 4.6 billion years ago, our corner of the galaxy was a vast, swirling cloud of interstellar gas and dust. Under the force of its own gravity, this cloud began to collapse, and at its dense, hot center, our Sun was born. The material that was left over formed a flattened, rotating disk around the young star. It was within this protoplanetary disk that the seeds of planets, moons, asteroids began to stick together through a process called accretion, slowly growing into larger and larger bodies. These growing clumps, known as planetesimals, were the fundamental building blocks of the planets. Jupiter's immense gravitational influence was a powerful disruptive force. It stirred up the planetesimals in this area, accelerating them to high speeds. Instead of gently combining, they began to collide with such force that they shattered, rather than merged. This process prevented a full-sized planet from ever forming in that gap. The asteroids we see today are the leftover remnants of this chaotic, planet-building era. They are the fragments of would-be planets that never came to be. Over billions of years, these bodies have continued to evolve. The relentless light and heat from the sun have altered their surfaces, a process known as space weathering. Countless collisions with one another have further sculpted their shapes. Some larger asteroids may have even undergone internal heating and differentiation, developing a core, mantle, crust, only to be shattered later, exposing their metallic interiors. Therefore, when we study an asteroid, we are looking at a pristine piece of solar system history. These objects have remained largely unchanged since their formation, preserving a chemical record of the early conditions of the protoplanetary disk. They are not merely rocks floating in space. They are precious artifacts that hold the clues to understanding how our own world and its neighbors were created. Every asteroid in our solar system is in constant motion, bound by the invisible but powerful force of gravity. Just like the planets, asteroids follow predictable paths around the sun known as orbits. Orbits are often very different from the nearly circular paths of planets like Earth. Many asteroids have highly elliptical or stretched out orbits. An asteroid's distance from the sun can vary dramatically over its journey. Its speed changes, accelerating as it gets closer to the sun and slowing down as it moves farther away. This complex ballet is dictated by the laws of celestial mechanics. The gravitational pull of the planets, especially giant Jupiter, shapes and alters these orbits. Jupiter acts as a cosmic shepherd, nudging and pulling on smaller bodies. That interaction can have profound effects. It can stabilize some asteroids, keeping them confined in the main belt for billions of years. Or a close encounter with Jupiter can act like a gravitational slingshot, ejecting asteroids onto new trajectories. Some are flung toward the inner solar system. Others are cast out into the cold, dark depths of space. That's why not all asteroids stay in the main belt. Trojan asteroids sit in stable points just ahead of Jupiter and behind Jupiter in its orbit. Others become near-Earth objects, or NEOs. These are asteroids whose orbits bring them into Earth's neighborhood, crossing our planet's path and demanding close attention. Asteroids are not all the same. They come in a wide variety of compositions, colors, and sizes, reflecting their diverse origins and histories. To make sense of this cosmic menagerie, scientists classify them into several main types based on their spectral properties, the way surfaces reflect sunlight. Here are the three main types. The most common group makes up over 75% of known asteroids, the C-type, or carbonaceous asteroids, extremely dark with a reflectivity like charcoal, considered among the most ancient objects in the solar system, containing large amounts of carbon, containing rock and minerals, chemically very primitive. The next major group is the S-type, or silicaceous asteroids, made primarily of silicate rock and metallic nickel iron, much brighter than C-types, dominant in the inner main belt, closer to Mars, likely fragments of outer rocky layers of larger bodies that experienced heating and differentiation. Their brighter surfaces contrast sharply with dark C-types. A third group is the M-type, or metallic asteroids, rich in metals, primarily nickel and iron, thought to be exposed metallic cores from shattered, differentiated parent bodies, essentially giant pieces of metal floating in space, of great interest for planetary science and for potential resources. Asteroid mining. Section 5. The Specter of Impact. Assessing the threat to Earth. The question of whether an asteroid can hit Earth is not a matter of if, but a matter of when and how large. Our planet bears the scars of past impacts. Geological history tells a clear story of their devastating potential. The most famous of these events occurred approximately 66 million years ago. A large asteroid, about 10 kilometers in diameter, struck the Earth in what is now the Yucatan Peninsula. The resulting impact created a cataclysmic chain of events, a massive explosion, widespread wildfires, and a global winter that blocked out the sun. This event is widely credited with causing the mass extinction that ended the age of the dinosaurs. Impacts of that magnitude are exceedingly rare, tens to hundreds of millions of years between them, but smaller asteroids hit far more frequently. Most are tiny and burn up harmlessly in our atmosphere, creating the beautiful streaks of light we call meteors or shooting stars. Slightly larger objects, several tens of meters across, can survive and explode in the atmosphere with tremendous force. In 2013, the Chelyabinsk object, about 20 meters wide, produced an airburst that shattered windows and injured over 1,000 people. This modern event is a stark reminder of the energy these small bodies carry. A significant asteroid impact on our modern interconnected civilization would be profound. A direct hit on a populated area would be catastrophic, causing immense destruction and loss of life from the initial shock wave and subsequent fires. Even an impact in a remote area or an ocean could have global consequences. An ocean impact could trigger massive tsunamis. A large land impact could eject dust and debris into the atmosphere to block sunlight, disrupting agriculture and causing temporary global climate change. The delicate infrastructure of our world is vulnerable to such a powerful natural event. This is why the study of asteroids is not merely academic, it is planetary defense. To protect Earth from a potential asteroid impact, we must first know what is out there. This is the mission of a global network of scientists and astronomers who operate a vigilant, around-the-clock watch of the skies. Their primary tools are powerful ground-based telescopes and space-based telescopes. These survey telescopes systematically scan large swathes of the night sky, taking a series of images of the same region over a short period. Sophisticated software then analyzes these images, searching for faint points of light that have moved relative to the fixed background of stars. These moving objects are the initial candidates for newly discovered asteroids. Once a potential NEO is identified, follow-up observations are crucial. Observatories around the world will quickly turn their attention to the new object to gather more data. By precisely measuring its position at different times, astronomers can calculate its orbit with increasing accuracy. For asteroids that do pass nearby, powerful radar systems can be used. Goldstone Deep Space Communications Complex. By bouncing radio signals off the asteroid's surface, size, shape, rotation, exact distance, velocity, refining its orbital prediction even further. Space missions provide another vital layer of information. NASA's OSIRIS-REx mission, for example, orbited the asteroid Bennu, mapping its surface in high resolution, collecting a sample to return to Earth. Japan's Hayabusa 2 mission accomplished a similar feat at the asteroid Ryugu. These missions help us understand the structure and composition of asteroids, which is critical knowledge for planning any potential deflection effort. All of this data from telescopes, radar, spacecraft is collected and analyzed by organizations like NASA's Planetary Defense Coordination Office, the Minor Planet Center. These international collaborations maintain a comprehensive catalog of all known asteroids and their orbits, continuously running simulations to identify any objects that pose a potential risk of impact. Finding a potentially hazardous asteroid is only the first step. The next is knowing what to do about it. Fortunately, if we have enough warning time, years or ideally decades, we have several viable strategies for deflecting an asteroid and preventing it from hitting Earth. The key principle is that we do not need to destroy the asteroid. We only need to change its velocity by a very small amount. Over a long period, even a tiny nudge can alter its trajectory enough so that it safely misses our planet. One of the most mature and well-tested concepts for achieving this is the kinetic impactor technique. A kinetic impactor is a straightforward approach. You simply fly a spacecraft into the asteroid at high speed. The collision transfers momentum to the asteroid, altering its course. The effectiveness of this method was brilliantly demonstrated in 2022 by NASA's Double Asteroid Redirection Test, or DART, mission. The DART spacecraft successfully collided with Dimorphos, the small moonlet of the asteroid Didymos. The impact measurably changed Dimorphos's orbit around its parent asteroid, proving that humanity has the technology to intentionally move a celestial body in a predictable way. Another promising method is the gravity tractor. This technique is more subtle and controlled. It involves positioning a massive spacecraft to fly alongside the asteroid for an extended period without touching it. The spacecraft's tiny gravitational pull, exerted over months or years, would be enough to slowly and gently tow the asteroid onto a new, safer path. This method offers a high degree of precision and is particularly well-suited for situations where a more forceful impact might risk breaking the asteroid into smaller, but still dangerous pieces. Scientists are also exploring other, more advanced concepts. These include using focused solar energy to vaporize material off the asteroid's surface, creating a gentle, natural thrust. In more urgent scenarios, the use of a standoff nuclear detonation could provide a powerful push without shattering the object. Each strategy has its own set of advantages and challenges, and the best choice would depend on the asteroid's size, composition, and the amount of warning time available. The ongoing work of international space agencies and scientific collaborations is focused on refining these techniques and ensuring that we have a robust toolbox of options ready, should the need ever arise. To convey the story of asteroids effectively, the visual presentation must be as clear and deliberate as the narration. The visual journey should begin with a wide, cinematic shot of our solar system, establishing a sense of scale and place. From there, we would smoothly zoom in, moving past the orbits of the inner planets to reveal the asteroid belt. This should not be depicted as a crowded field of rocks, but as a vast, sparse region where countless bodies are moving on their own distinct paths. This realistic portrayal is crucial for building credibility. Slow, graceful camera moves should be used throughout, giving the viewer time to absorb the information and the grandeur of the scenes. Close-up shots are essential for illustrating the diversity of asteroids. C-type, the dark, almost black surface, peppered with craters. S-type, the brighter, brownish-gray surface, littered with boulders and regolith. M-type, the distinct gleam showing metallic composition. We should show an asteroid tumbling slowly in the silent vacuum of space, highlighting its irregular shape and motion. When discussing missions, we should show a spacecraft's careful approach, its intricate dance as it orbits the asteroid, and perhaps a gentle landing to collect a sample, emphasizing the precision of these robotic endeavors. To explain complex concepts like orbits and gravity, simple, clean graphics are indispensable. We can superimpose glowing lines over realistic space backgrounds to trace an asteroid's elliptical path. An animation could show how Jupiter's gravity slingshots an asteroid onto a new trajectory that crosses Earth's orbit. For the detection section, we can show the perspective of a telescope, with a star field where a single point of light moves between frames. We can then transition to radar screens displaying the rotating shape of an asteroid, and scientists in a control room, analyzing data and collaborating. Throughout this entire visual narrative, the auditory experience must remain focused and uncluttered. The only sound should be the narrator's calm, deep voice. There should be no music, no sound effects, not even the manufactured whoosh of a spacecraft. The silence of space should be a key element of the presentation, allowing the narrator's words and the power of the visuals to carry the story. Clear, easy-to-read English subtitles should accompany all spoken text, ensuring that the information is accessible to everyone. This minimalist and authoritative style builds trust and allows the profound nature of the subject matter to speak for itself. That's the idea. In our journey through the cosmos, we have seen that asteroids are far more than just distant rocks. They are fundamental pieces of our solar system's history, time capsules that hold the secrets of planetary formation. They represent a potential resource for the future and a potential hazard from the past. They are a constant and powerful reminder that we live within a dynamic and ever-evolving cosmic neighborhood. They have shaped life on Earth before, and they will inevitably cross our path again. However, unlike the dinosaurs, we have the ability to see them coming. We have developed the tools of science, telescopes, radar, spacecraft, that allow us to find and track these objects with remarkable precision. This knowledge is our greatest asset. Early detection is the foundation of our planetary defense, giving us the most precious resource of all time. With enough time, we can act. We can prepare. We can ensure that our future is not dictated by a random cosmic collision. The work to protect our planet is a global endeavor. By continuing to watch the skies, to study these ancient wanderers, and to prepare for any eventuality, we are taking responsible stewardship of our home world. The future is not written in the stars, but in the knowledge we gather from them. Thank you.